All right, the next topic, welcome back. The next topic is analog filters. And let me introduce the need for an analog filter. Let's tell you what it is, why we need it, and how. Okay. Let's start with what? There are three classes of analog filters that we're interested in. If we look at the gain versus frequency response, we could have something that looks like this, and that's called a high-pass filter. We're going to use a high-pass filter whenever we don't care about DC. Examples are sound and electrocardiogram. These are examples where the information is not encoded in the DC, in the zero frequency component. That's just nonsense. I don't care what the atmospheric pressure is in the room. I just care about the variations in pressure generated by the sound. The second is a low-pass filter. Again, gain versus frequency. And we're going to use the low-pass filter for two reasons. One is to reduce noise. And so if it turns out that that signals out here are noise, I can use a low-pass filter to remove it. Okay? It turns out you could have used a digital low-pass filter to remove this as well. But the second reason I'm going to use a low-pass filter is called anti-aliasing. In essence, the Nyquist theorem tells us that if I'm interested in 0 to F frequencies in my signal, my sampling rate must be strictly greater than twice that largest frequency component. Okay. All right, now the flip side is what happens if the input is a very high frequency and above 1/2 Fs. So let's re-look at the problem. We have our input here, which goes to a transducer. Okay. The transducer converts the input to an electrical signal, and then we have our entire circuit right here. This is our circuit, the amplifier, etc. And that goes to the A to D converter. Okay. And you remember the A to D converter is going to be sampled at Fs. That's how many samples per second we're going to calculate digital numbers. Now, if we call this number Z right here, this input to the A to D, and we look at it with a spectrum analyzer. Now, a spectrum analyzer is going to look at the amplitude of Z, okay, amplitude, okay, as a function of frequency in hertz. And this axis here is going to be in hertz. But this axis here could either be in volts or it could be in decibels. Okay? In both cases, what we have is large amplitudes and small amplitudes. And one of the interesting points on this axis is this line right here. Okay? And we look at the resolution of the A to D. Now, if this resolution is in volts, it's simply 3.3 volts over 4096 of precision, about a millivolt. But if it's in decibels, the way we're going to calculate this is the amplitude in decibels is going to be 20 log base 10. Now, it's 20 because we're looking at volts. And then we're going to compare the amplitude of this signal, which is 3.3 volts, divided by 4096. But we can't take the logarithm of a volt, so we're going to compare that to the full scale. Okay? So what we have here essentially is the calculation of what is this point here, 20 log base 10 of 1 over 4,096. And now the interesting part about this curve is to think about the three regions defined by, on the amplitude axis, where we're going to define the resolution. And on the frequency axis, I am interested in 1/2 fs. That's the aliasing cutoff. And if we look at the signals here, okay, what we think about are, what if the input to the A to D converter oscillated less than a millivolt, less than 1/10 of a millivolt, at a microvolt, a picavolt, a nanovolt? The digital samples would not see that oscillation. So we're going to classify this region of this spectrum as undetectable, okay, and not worry about it. But what I'm going to do is divide the other two into what I would say the good region here, okay, and this represents large amplitude, low frequency signals that are properly sampled. But the problem is this region over here, the bad region. What we have are large amplitude, large frequencies, and this is aliased. Okay? And so the way we're going to remove aliasing is to add an analog filter. Okay? We're going to add an analog filter. Can't be digital, such that it will pass. So if we look at the gain versus frequency of this analog filter, we're going to pass the signals of interest, 0 to F maximum, and we're going to reject the high frequency signals above 1/2 fs. So if we were to have an input presented at the A to D converter that would have otherwise aliased, the analog low-pass filter will pass these, okay, and then reject and prevent the aliasing. So in summary, we need the analog filter to remove aliasing. And we're going to do that by rejecting frequencies above 1/2 fs. Okay? That's the essence of what we're doing. We had that. What was this? We had this. What was that one? What's the first one? Mm-hmm. Oh, yeah. Drew it backwards. Yeah, smart. Good thing I didn't write what it was. That's a low-pass filter. And why did we have low-pass filter? Two reasons. Reduce noise and to prevent aliasing. Okay? And this one is a high-pass filter. Why did we have it? Throw away the DC because the DC has no value. Now, if you go to Lab 9 and you're measuring temperature and you use a high-pass filter, we're gonna laugh at you. Just saying. Trying to measure temperature in this room, right? It's 75 degrees, the perfect temperature, Fahrenheit. I'm going to laugh at you if you use a high-pass filter. Why? You just threw away the data and just kept the noise. Right? That's a noise to signal improver. Right? Be careful. Thinking is required, okay? Sometimes we have them both, okay? Sometimes we have what's called a bandpass filter. And as it turns out, the EKG and the sound actually use both a high pass and a low pass, because we want to throw away the bad stuff, the DC, but we also want to anti-alias. Okay? But we're going to focus on these two up here today, the low pass and the high pass.
You can really understand how these filters work. Okay, again, this is 445L. I'm going to give you an equation. You're going to fill in numbers. I mean, I'm going to give you a circuit. I'm going to give you a template of a filter, and you're going to fill in the numbers. Okay, it's not a blank sheet of paper circuit design class. There's 4 or 5 or 6 or 7 different analog circuits we're going to use all semester, and your job on the test is to figure out which one goes in the box. Now, with life, for me, the box just gets bigger because there may be thousands of circuits out there, and I'm just going to pick the one that I like best and then fill in the box. Okay? But I'm going to understand the box simply here by knowing the impedance of a capacitor, right? The impedance of a capacitor, which is 1 over j omega c. Okay, so if we start with this fundamental thing where omega is 2 pi f, and j is obviously the square root of -1. We can really understand how all this stuff works. And you remember my rule about capacitornesses. At DC, how does this circuit behave? This circuit here at DC behaves in what way? Okay, it's just a resistor, right? R2. Okay, and at AC, at very large voltages, how does it behave? Short. That's short. Okay, see that? And so, on the test, I could give you this one and ask you the same question. How does it behave open? How does it behave at DC? How does it behave at AC? I could. I'm not. So I can take that and stick it in a circuit that I already know. Okay? And the way this circuit works is if I think of it without the capacitor, if I just sort of ignore the capacitor for a moment, this is a linear amplifier with offset. Okay, it's one of those circuits we did a couple of times ago. But the gain of this circuit at DC is what? What's the ratio of the amplitude, right? V out equals what function of V in? You see that? It's going to be, the gain here is going to be -5 times V in plus an offset. That's how this is going to work. The ratio of those two resistors. But you remember at very high frequencies, right? This 5 is the ratio of R2 over R1, right? That's that ratio. So at very high frequencies, how does this behave? What happens to the effective impedance of those two resistors at very high frequencies? Right? Capacitor becomes a short, R2 becomes 0, and so the gain is 0 over R1. Okay? Nothing. No output, no effect of the output from the input. And that's what happens when it goes from DC to very high frequencies. Okay? Is it goes from a gain of -5 to a gain of 0. Well, if I plot that in the gain versus frequency plot, and I do it in decibels, where -3 dB is, that's whatever, 7 over 7, we see that there will be a spot in which it fits 1 over the square root of 2. Okay. And that spot is going to be called the cutoff frequency. And it's going to be 1 over 2 pi R2 times C. Okay? Very, very simple low pass. So we can take anything that has gain and make it a low pass filter by putting a cap in series with the feedback resistor. Not a very good filter, but not very expensive either, right? All it was added a cap. How about this one here? Okay, this one here is not too complicated. I'll simplify it a little bit. Okay. Again, you want to do your what's the I can look at the AC and the DC component. How does this behave at DC? We've actually solved this in the microphone circuit, by the way. How does this behave at DC?
Doesn't really behave.
It doesn't behave at all, right? So the output is 0, okay, at DC. No current through the capacitor, so the output will become 0. Okay? But how does it behave at AC? It passes, right? Signals go through there at AC. So this has a gain versus frequency response that looks like that. And right there, this cutoff frequency, which is the point at which the gain is 1 over the square root of 2, or minus 3 dB. Okay? It's voltage gain, so it'll have the 20 log in there. That this is 1 over 2 pi times RC. Okay? If I add a V reference right here, it'll just float up to, it'll still have this gain versus frequency response, but it'll always be shifted up to right on top of the V reference, which we need to do because I need to get this voltage between 0 to 3 volts. Another way to do that is to do this way. Again, the effective impedance to ground here is going to be R, okay, because 2R in parallel with 2R. Okay, again, it's a linear circuit, so the first rule of linear circuit design is what? If I have multiple sources? Superposition. So let's just look at this from a DC component. From a DC component, this guy is blocking. So what's the output at DC? All right? 1.65 volts. Okay, but at AC, I have two sources. Right? I have two sources. I got the 3 volt source and the I get the 3 volt source and the input. So law of superposition says I can look at the response of Vn by analyzing that circuit here. If I look at just Vn and I don't look at the 3.3, I'm going to ground it. And so if this is 2K and this is 2K, I'm going to get that effective circuit. Okay? Again, that's a high-pass filter. If I want a little bit better high-pass filter, this is a front end that you see a lot in EKGs. Again, its purpose is it's a differential high-pass filter. So the signal V out minus V1 minus V2 is the signal, but now I have the signal pass through this filter, but still differential. So this is the input stage of EKG. All right. So those were this is as complicated about a high-pass filter you're going to get in this class. And if you want to learn better ones, just go take 438 or 438K. And you can design better high-pass filters. That's going to be good enough for me all semester. But for low-pass filters, we can actually have a lot of fun designing one more template for you. Okay, in order to understand this circuit, let's write it. Let's use our op-amp rules on this circuit just to get a flavor of how it works. First of all, it is a linear circuit. Do you see the negative feedback? You see it? Right there. There's the negative feedback right there. And now I can use my, this is going to be a low-pass filter, but it's going to have some awesome gain. It's going to be what's called a two-pole, which means it's going to drop off way faster than the other low-pass filter. And it's going to have this response. Okay? But let's understand how it works. What can you tell me the DC response of this is going to be? Let's just do the DC response. Okay? At DC, what does this do? It's a buffer, right? Yeah, the capacitors are open. Right? These are open.
So if this is the input, there's the input, there's the input, there's the input. It just input goes to output. It's got a gain of 1 at DC. See that? What does it do at very high frequencies? What happens to the capacitors? Right? What happens to the capacitors? They're short. Okay? They short. And in particular, what does C2 do? This one here, I'm sorry, not 2C, this one. What does this capacitor do at very high frequencies? It shorts. So what voltage is here? 0. So what voltage is here? 0, so 0. Okay? At very high frequencies, this thing goes to a short. In other words, no gain. But in between, okay, all we need to know is the impedance of this capacitor. The capacitor is J omega C, okay, the impedance of it. And so in order to study or in order to prove this circuit, all I need to know is this equation and a bunch of algebra, and I get the following design rule. Okay? And that is this particular template here will pass 1 radian per second. Now, nobody has 141 microfarads. Okay, that's way too big. But this particular circuit here, when R equals R and C1 is twice as big as C2, this template, which is called a Sallen-Key, and the formula is made by, was designed by this guy called Butterworth, and it has this shape. Now, it's not the best filter, but the math is easy, because all I have to do to tweak this circuit is to take my cutoff frequency. In other words, I could take something like 40 hertz, okay, because I want to get rid of everything bigger than 40 hertz. I divide the capacitors by 2 pi FC, and then I'm going to find a resistor. If I take this whole thing, right? If you look at all the equations that we had, right? All the equations we saw were a function of R times C. So what happens to these circuits if I multiply R by X and divide C by X? I get the same thing. And so I'm going to reduce the capacitors by X and multiply the resistors by X, and boom, I have a circuit. Okay. In order to make this real easy, there's a spreadsheet for this in here, and so we will next time we're going to talk about. We'll go back to the Nyquist theorem, and we'll talk more about data acquisition from a system standpoint. And I'll design you a filter next time using this.